In this work, we present an efficient real-time AI framework for sparse spatiotemporal data. To efficiently model point-to-point dependencies, an AI model should satisfy 4 key properties. It needs to be sparse, recurrent, parallel, and local. Linear attention and state space models satisfy 3 of these properties. They are sparse, recurrent, and GPU parallel. However, they lack locality. Moreover, modeling the entire image requires a larger internal memory to store diverse spatial patterns, resulting in increased computational cost. Convolutional local linear attention, which applies a positional embedding kernel to each local region, is computationally expensive. Therefore, our goal is to incorporate locality into linear attention and state space models without relying on convolution. Next, we present CoLA, a convolution-free local linear attention method. The key idea is a specialized local positional encoding kernel based on rotation, which can be decomposed into global positional encodings applied to the query and key. For simplicity, we assume that the query and key dimensions are 2, and the value dimension is 1. We define the kernel as a rotation in the feature space, where the rotation angle is linear with respect to the local coordinate. Due to the linearity of the rotation matrix, this kernel can be decomposed into 2 rotation kernels defined in the global coordinate system, which are applied to the query and key. Consequently, only local summation is required, rather than convolution. CoLA inherits the recurrent parallel property from linear attention while introducing locality. This is the CoLA module. Given the precontracted key-value matrix, we first perform spatial contraction using local summation, followed by temporal contraction via an associative scan to compute the state at each time step. This is a demonstration of convolution-free local feature extraction. It shows that CoLA extracts edges without relying on computationally expensive convolution. Next, we demonstrate equivariant feature extraction. A function is said to be equivariant to a transformation if applying the transformation before or after the function produces the same result. For example, convolution is translation equivariant. This is a demonstration of scale equivariant feature extraction. CoLA effectively achieves scale equivariance because it does not rely on fixed-size kernels, but instead uses a functional representation. Here, we demonstrate rotation equivariant feature extraction. CoLA effectively achieves rotation equivariance because it does not rely on fixed-size kernels, but instead uses a functional representation. This is an experiment on corner tracking using a sparse event stream. It shows that CoLA achieves comparable accuracy with low computational cost. Here is an ablation study on video reconstruction from a sparse event stream. Without locality, the model fails to reconstruct the video. In contrast, our local method, CoLA, successfully reconstructs it. We evaluate the contribution of CoLA to image classification and large-scale vision foundation model distillation tasks by replacing softmax attention with CoLA in a VT-tiny model. CoLA outperforms softmax attention on both tasks. Interestingly, CoLA achieves performance comparable to local convolution at test time, despite strong constraints on the kernel pattern.